Ultraviolet catastrophe, a problem which puzzled physicists for decades during the mid 19th century. It was the first physics problem ever, which couldn't have been explained by classical physics. Classical physics just failed explaining this problem, and it gave us an insight to a whole new different type of physics involving things which are billion times smaller than a grain of sand, called quantum physics. So you see, during the mid 19th century, physics was expanding. On everyday basis, physicists were encountering new physics problems and were solving them. One such problem was this ultraviolet catastrophe. In between the 19th century, when the famous physicist James Clerk Maxwell had brilliantly discovered that light was made up of oscillating electric fields and magnetic fields, which are perpendicular to each other. So after people knew that light was an electromagnetic wave, and different colors of light were made up of different frequency waves that had their own wavelengths. But one thing which made physicists curious was that they wanted to know that how much light of different frequencies and different wavelengths was being given off by a hot filament as a function of its temperature. Now what I mean by this is that they wanted to know that how can the gain or loss in temperature would affect the frequency or the wavelength of light being emitted by a hot filament. In order to understand this, physicists made or coined a theoretical object. They made a theoretical body called a black body. This theoretical object was said to absorb 200% of visible light. Now obviously it is impossible to make such a thing that could absorb all light. As I said, then it was a theoretical object made by a physicist. Even the blackest blacks on earth, like the Vanta black, which is made up of carbon noodles, isn't able to absorb all light. It's only able to absorb about 99.96% light. Rest 0.04% light is just reflected into the atmosphere. Now back to the main thing. Just imagine if you take that black body and if you keep it in an environment where the temperature of the surrounding environment is greater than that of the black body itself. So obviously the black body will keep on absorbing heat from the environment in the form of infrared radiations until it reaches something called a thermal equilibrium, where the temperature of both the black body and the environment will be the same. So it seems as if a black body is a perfect absorber of radiations. It can absorb radiations. But in reality, it's also a perfect emitter of radiations if the internal temperature of the black body is greater than that of the surrounding medium. So in this case, the radiations will be emitted out of the black body until it reaches the thermal equilibrium. Now this radiation which is being emitted out by this black body is something called black body radiation. Now physicists, as I said, wanted to see and calculate the frequency and the energy of this radiation which is being emitted by the black body radiator as the temperature rose. So what theoretical physicists theorized was that as the temperature increases or as the thermal energy increased within the black body radiator, so the frequency or the energy of light which is being emitted by the radiator also increases. So if the temperature increases, so more and more of higher frequency waves like the ultraviolet rays, X-rays or even the gamma rays will be given off, which have shorter wavelengths, higher energy and higher frequencies. Now if we were to draw this out on a graph, where on the x-axis we will have the frequency of light being emitted and on the y-axis we will have the intensity of energy, which is energy provided per area per second. Now according to what theoretical physicists suggested was that this graph will have an ascending curve. So as the energy provided will be more, higher frequency waves which have higher energy will be given off. But this thing actually contradicted a lot of other things. First of all, what was suggested was that infinite amount of higher energy waves will be given off. This thing conflicted the idea of the law of conservation of energy. And also the experimental results were completely different from those based on certain theories. What experiments found out was that the same graph would first take an ascending plunge and then it will descend downwards. Then one famous physicist named Max Planck, who did all those experiments, what he did was that he threw the existing theory out of the window as an act of despair and gave his own explanation, which would explain the experimental results. What he suggested was that light emitted by the black body radiator was in discrete chunks. So basically, what he wanted to say was that light carried energy in pockets or quantas, where large pockets of energy were being carried by higher frequency waves and smaller pockets of energy were being carried by lower frequency waves. For centuries, people thought that a photon of light can have any frequency. But the idea of light energy being quantized showed us that there were only specific energy levels, some specific energy levels where a photon can accommodate. And there were only some specific values of energy which a photon could adopt to. Now you see, what classical physics suggested was that a black body can radiate large amount of ultraviolet radiations. But what experiments showed us was that the black body could radiate relatively less amount of ultraviolet radiation as compared to what classical mechanics suggested. And the reason for this was that higher frequency waves like ultraviolet rays carry large and only a specific amount of energy. And they were very typical about the quanta or the pocket of energy which was being carried by them. So they were like fuzzy kids, very choosy and very typical. So these rays tend to lose out of the energy being emitted by the radiator, since the energy distribution within the black body radiator was not uniform. So most of the energy was being carried off by lower frequency waves, which accepted the idea of sharing and tend to share the amount of energy they carry. And in fact, this is what temperature is. This is the scientific definition of temperature. Basically, it is the average amount of energy which was being emitted by something in form of different frequency waves. Later on, Max Planck gave his formula that energy is equals to the Planck's constant times the frequency of light, where he showed us that energy which was being carried off by the light waves was directly proportional to its frequency. So higher frequency waves had a higher energy and lower frequency waves had lower energy. At the end, Planck suggested was that any light bulb filament should be heated up to 3700 kelvins, so as that most of the light was being given off in form of visible light. Because at this temperature, all the different frequencies of light, the higher frequency, the lower frequency and the mid frequency, were being given off in equal amounts. So most of the light was being given off in the visible part of the spectrum, not in the invisible part of the spectrum at this temperature. So in the end, Max Planck solved the problem to the ultraviolet catastrophe, and he gave his quantum theory, which we now know as Max Planck's quantum theory. And he basically solved the problem which puzzled physicists for a very long time. Now, what I found interesting about this problem was that initially Max Planck didn't had the intention to solve this problem. He was actually trying to figure out a completely different thing. He was trying to figure out how did the heat transferred from hotter objects to colder objects. But in doing so, he found out the solution to a completely different thing which has immense importance in modern physics. Now, apart from that, what I found interesting about this problem was that it also shows the importance of experimental learning. Just imagine if Max Planck wouldn't have done all those experiments during the 19th century, then we wouldn't have known quantum physics. Quantum physics would just have been another word for us. But see how the importance of experiment has led to the world of quantum mechanics. And this is what I like about this. This is what, when you experiment, you try to figure out things and you end up having different observations as compared to what theory suggests. And that changes the whole thing. So, well, that's for now. I'll meet you in the next video, and bye. Thank you.